Here we have the homework number 5 about the guided CTLA design. This homework is a guided design exercise of a CTLA for a 56 gigabit per second PAM4 receiver through an 8 dB loss channel. Most of the important design parameters and the conditions are given here. So you're expected to follow the guided design flow and apply the first order equations and develop intuition about how the key CTLA parameters affect bandwidth, the gain peaking, bias, headroom, and so on. Here you have kind of trivial questions about the symbol rate and the Nyquist frequency of PAM4 data. And since the source degeneration network is given, meaning that we already have the RS and the CS values provided, we can calculate the zero frequency according to this equation. And we choose the unity gain frequency, targeting sufficiently high frequency such that the output bandwidth is not limited by the GM device itself. And here we estimate the GM that is required to achieve the chosen target unity gain frequency. And here, using the GM and the degeneration resistor, we get the boost factor, and then we calculate the first pore frequency. And then we want to calculate the load resistor value and the low frequency gain. Here we calculate the input device voltage bias condition and verify if the devices are in saturation with how much margin. And we do the same thing for the current source devices. So here we have the solution to the given exercise. So let's go through this. Since the PAM4 symbol delivers 2 bits of data per symbol to achieve 56 gigabit per second of data rate, we need a symbol rate of half of the data rate, which is 28 gigabaud. And the Nyquist frequency is simply half the baud rate. So we have F Nyquist of 14 gigahertz. And we place the source degeneration 0 using RS and the CS values. Using this first order equation for the zero frequency, we obtain approximately 5.57 gigahertz, which is about 40% of the Nyquist frequency, which was our initial assumption when we calculated the RS and the CS. And this means that the CTLA will start equalization gradually from around 5.5 gigahertz. After placing the 0, we estimate the unity gain frequency required for this CTLA. As a practical design heuristics, we choose the unity gain bandwidth to be approximately 2.5 times higher than the Nyquist frequency. Since the Nyquist frequency is 14 gigahertz, the target unity gain frequency becomes approximately 35 gigahertz. And this provides sufficient bandwidth margin while still preserving meaningful amount of gain peaking near the Nyquist frequency. And then we estimate the required transconductance value from the unity gain frequency and the load capacitance. So using this relationship, we can calculate that the required GM is approximately 22 millisiemens. And the transistor level simulation also gives us about a GM of about 22.8 milliS, which is very close to our estimated value. Now we estimate the small signal response. The source degeneration network creates gain peaking, and the boost factor is approximately 4.75, which can be calculated using the GM and the RS values. And this corresponds to about 13.5 dB in the dB scale. And using the boost factor and the zero frequency that we targeted earlier, we can estimate the frequency of the first pore. And then we extract the load resistance value from the DC operating point. Using the supply voltage and the output common mode voltage and the branch current, we can calculate the load resistance to be approximately 148 ohms. And then using the first order gain equation, we can estimate the low frequency gain of about 0.7, which corresponds to minus 3.24 dB in the dB scale. After estimating the AC behavior, we should verify if the DC operating conditions are reasonable or not. So first, we check whether the input differential pair transistors are remaining in saturation. So using the output common mode voltage and the source potential value, we can calculate the available drain to source voltage margin. And since the actual VDS is much larger than the VD set, we can conclude that the input transistor safely remains in saturation under the 1 volt supply condition. And then we verify the headroom of the current source devices. The current source transistors also remain in saturation. However, now the margin is quite small. This is a common challenge in low voltage, high speed design. As the supply voltage decreases, maintaining sufficient headroom while preserving sufficiently high gain and bandwidth becomes increasingly difficult. And finally, here we verify the CTLE operation using the cadence transient simulation and eye diagrams. Here we have the closed eye diagram from the channel output, and after applying the CTLE with the design parameters that we obtained and assumed, we have the eye openings much better than without the CTLE.